Okay, good morning. Today is really our last full technical lecture. I might try to add a bit of content in on Thursday after we go through our homework, if possible, because today we've got all of advanced oxidation processes to go through and ozonation, which is somewhere between a disinfectant and an advanced oxidant. And so I've got way too many slides to present today. So I'm gonna go quickly and just see where we get, all right? And I think the most important sort of technical aspects to consider when we are thinking about applying advanced oxidation processes are towards the front. So I think we'll get through all that stuff that I feel is most important, and at least enough to give you a feel for how, let's say if we talk about, for example, hydrogen peroxide and using UV to split it or using other methods, then even if we don't get to the Fenton processes, which is using iron as a catalyst to decompose peroxide or something like that, you'll still have the same concepts ready and at hand. And I'll post all these slides. But okay, so with that, I'm going to dive right into it, and we'll start talking about ozone. So it was actually first used 1893 in the Netherlands, and then in France in 1906. And it's generally a gas, but as we'll see in a minute, it has very high solubility in water compared to oxygen. So we can apply it pretty well. So typically we will generate it on site in terms of to make it a little bit safer to ship, or to avoid shipping and all of that. Ozone reacts pretty quickly, so it will decay faster than chlorine, so it's definitely not something we'd leave in the pipes for a residual. And we can use it for disinfection, for degrading taste and odor and color sometimes. So we can use it for a lot of things. Could be for oxidation reactions, the same types of redox stuff we were talking about. Even simply oxygenating can work on some things. Well, all the more effective would be ozone. And then, of course, advanced oxidation processes, AOPs. Ozone can be used for several, as we'll see. Okay, so a few characteristics of ozone. It is colorless. It does have a bit of an odor, so if you ever used like a cleaning spray that contains some ozone, you might recognize it. It's a little bit sweet, metallic, a little acrid or pungent. The solubility at 1 atmosphere is 450 milligrams per liter, whereas oxygen is, in equilibrium with the atmosphere, oxygen is something like 8 to 10, maybe up to 15 if it's cold. We'll just say 8 to 15 milligrams per liter for O2, but that's in equilibrium with the atmosphere that's 20% oxygen. So if we had 100% oxygen, it pushes oxygen up to maybe 40s, I think, milligrams per liter, but still ozone is 10 times that. Okay, so pretty strong amount. So we typically would apply it at less than 12% ozone, and that brings us to a point where usually the practical applications are performed with 2 to 3 milligrams per liter. So we're not usually going super crazy with it, but as you know from the solubility discussions we've had, it does go into water pretty easily, and it's happy to stay there compared to oxygen at least. Okay, a few methods to create ozone. We could take clean, dry air or pure oxygen. Either one's all right, but we want to keep it dry to avoid formation of NOx, so the nitrous oxides, and therefore nitric acid, because the process would generate those types of species. In the presence of water, you'd get to acid. So typically, this corona discharge, you take an electrical arc, and essentially it's a lot like lightning, and you're creating this voltage across some material. It's exposed to the air, and that's going to allow for the creation of ozone chemically in the gas phase. so the frequency in this case of the alternating current would have some relevance to the production rate. So you could go really high frequency and get large amounts of production here. You can use ultraviolet light. In fact, when we say vacuum UV, we're talking typically about ultraviolet light that you really can only utilize or measure or observe if you're in a vacuum, because oxygen and ozone and other stuff in the atmosphere, the gases will absorb it too strongly. So this would be something like 120 to 180 nanometers is typically what we refer to as vacuum UV. You can use that and expose oxygen to that, and you're splitting the oxygen, creating these oxygen radicals that will go then react with more molecular oxygen, and you'll end up with ozone. This is actually what's happening in our upper atmosphere. This is why we have an ozone layer. It's because we've got all this UV coming in, all sorts of photochemistry happening. A side note, if you were to go up and hang around in the upper atmosphere, well, it's a pretty thin atmosphere, so there's actually not a lot of gas, but the gas that you'd be exposed to is undergoing a lot of photochemistry. So way up there, you'd really want a lot of protection from UV, as well as maybe some way to be protected from the radicals you'd be exposed to. Okay, so the UV method is not quite as efficient, and as you can imagine, if ozone's also absorbing the UV, you're having production and consumption at the same time. But this one does not produce NOxes, so that's some benefit. Okay, I've got a little video here that I realized I hadn't looked at in quite some time, but I want to share it. I need to pull it up on a web page, showing lightning, and it's a good example of corona discharge. When I was in grad school, I found this astronomy picture of the day website. It's like a NASA website or something, and just fascinating stuff here. So let me see if I can get this. Sorry about the microphone. So this is a really, really slow motion lightning strike, and I thought it was really fascinating to watch the little streamers come through down like that, and then one makes contact, and then the lightning kind of strikes backwards up from it. So just to imagine what corona discharge is looking like and why we form a lot of ozone during lightning storms. Oops. And if you ever need a random interesting sciencey picture for the day, check out NASA's astronomy picture of the day website. Okay, so a few other techniques we can form ozone. There's a cold plasma technique. It's kind of expensive, uses pure oxygen, and you can generate up to about 5% ozone. Electrolytic, we can split water into hydrogen gas, oxygen gas, and ozone. You'll end up forming all three. You can get up to about 20 to 30% ozone concentration there. You have to use quite a lot of overpotential, so higher voltage than you would normally. And you really just can't store ozone very long because it's just going to decay into oxygen ultimately. So you don't really have too much of an opportunity to store and ship it. And even if you did, it would be pretty, there'd be a lot of hazards involved because it's a highly oxidizing substance. Okay, if you wanted an example problem for ozone transport, I just went ahead and left notes here from last time. This is actually from the book that I use for undergraduate class. So this is a pretty simple plug flow reactor example. What happens if you ozonate add ozone into a pipe that's coming into to be treated, maybe it's sort of a pre-treatment step, and you're wondering how much ozone do you have to add at the front, you know, some half-life about it. So feel free to take a look here if you want sort of a little bit of refresher practice. Okay, so when we create an ozone contactor, it'd be a lot like our typical disinfection reactors, except that we're constantly bubbling water through them, or excuse me, bubbling the ozone through them, the ozone in the gas. And so instead of just having a typical plug flow reactor where your water is just carrying about its merry way, you have mixing along the way. So it's a little bit more like this whole section or segment would be pretty well mixed. So it's somewhere between a plug flow reactor and a CSTR. In fact, you might say to yourself, well, maybe each half of the pipe segment, each one of those is a CSTR, and so then we've got what 10 or 12 CSTRs in series here, or maybe you just say each segment of the pipe here, each turn or each segment would count, each row here. So you could look at it as one big PFR, but that's probably not going to be the best. So instead, you might look at it as a series of CSTRs. Okay, so we talked about that in the past where we said, imagining a case where we have some number of bacteria and we're splitting it kind of each row sort of a thing. We'd have N0 coming in, N1 going out, which means N1 coming in to the next, or excuse me, that would be, we're heading from right to left here, so this would be N1 going that way, N2 coming out here, which would then go into here, and it would, you know, continue as you might expect. And then we'd have some N final. And if we had a system like that and we were doing CSTRs, if we could make some assumptions that they're all the same, so if tau1 equals tau2, and the volume of each of these were the same, then ultimately we could set up an equation saying that if we want to find the final concentration compared to the starting one, we can get there by a system of essentially pairing all these reactors in place to cancel out ultimately to get N5 over N0. Right. Each of these reactors we could put in that way, and once we do that, everything will cancel except the N5 and N0. To write that, if we were to solve the mass balance, the mass balance on a CSTR in this sort of manner at steady state, a very simple system, we'll remember we would say that N over N0, if we solve it that way, would be 1 over 1 plus tau k. Yeah. So that's all from early on in the semester, and I think we already looked at this type of a problem, but here's a time in which it would make a lot of sense to approach it in this manner, right? And so then for N5 over N0, that would look like if all of these are actually the same reactor, the same proportion of stuff is going to degrade in each one of them. We'd also have to keep our concentration of ozone the same. So really we'd also put a C here for ozone, and a C O3 is constant. Then we would have this equation where we'd have 1 over 1 plus tau k times C for the ozone, all that to the 5th power. Or, yeah, it should be 5th. Okay, make sense? All right, so just wanted to call your attention to that example. We talked about that concept before. Got an example for you here if you wanted to solve. Again, I left whatever notes I had from last year up. May not have solved for the part B, but I'd kind of just showed you the mechanism. So feel free to quiz yourself on this in your own time. Like I said earlier, I'm just going to rush through as much of this as we can and see where we get. Okay, there's part B. Okay, so if we use ozone as a disinfectant, there's a few key reactions. And first of all, I'll note that, so it's going to be a direct oxidation type of scenario. So it's going to directly attack the organic matter of whatever microbe that we're trying to destroy. It's really quite effective against cryptosporidium, especially in comparison to chlorine, which is not very effective. So cryptosporidium can form these cysts that protect themselves from the environment. And so they're pretty well protected against free chlorine, not so well protected against ozone. It'll have direct reactions with many organics, whether that's organic chemicals or organic molecules in a microbe. And it can also undergo reactions with even just hydroxide in solution to form some radicals that can get us hydroxyl radicals that can be quite reactive. Okay, so ozone, it could just directly react. It could decompose to form this hydroxyl radical. Hydroxyl radicals are pretty well known to be one of the strongest oxidants, strongest naturally occurring oxidants. In atmospheric sciences, it's known as the atmospheric cleansing agent. So it goes around oxidizing stuff. So if you ever hear about the typical lifetime of methane or CO2 in the atmosphere or something like that, there are natural processes that can bring things out, but something like methane would be ultimately oxidized to CO2 over some amount of years, largely due to reactions with hydroxyl radicals. So if there's something around that's doing the task of oxidizing really difficult stuff, it's probably trace amounts of hydroxyl radicals. Okay, so hydroxyl radical could then react with this as an indirect oxidation of the substrate by hydroxyl radicals, meaning indirect from ozone. Hydroxyl radicals then directly reacting with it, but ozone causes an indirect oxidation by formation of the hydroxyl radicals. Alternately, sometimes these hydroxyl radicals could be scavenged by things that just take it and don't really do anything else with it. They're just consumed. Okay, so the radical formation pathways, here's a few. If we have ozone reacting with hydroxide, we can get two oxygen diradicals here with the O2 minus plus H plus. From there, that can react to give us some sort of a ozone minus radical and oxygen. That can get us this guy here, which can finally then decompose into oxygen, molecular oxygen, and hydroxyl radicals. So it's a little bit convoluted. There's a lot of steps here, but we see we can get to the hydroxyl radical, and it's going to be dependent on pH because it depends on the amount of OH minus. So at high pH, this is going to be more likely to happen. Low pH, we're not going to have so much of it. And finally, we can get the net reaction down here at the bottom. 3 ozones plus 1 OH minus and 1 H plus would give us 2 hydroxyl radicals and 4 molecular oxygen. Okay, I mentioned this a moment ago, but we often have participation of other stuff, quenching agents, stuff that just happens to be in solution. We would maybe call it M. So if we think about ozone scavenging, and this would be a similar feature for other reactants, other radicals and oxidants. If we have some solute M that's going to react with our ozone, in this case, O3 plus M might give us a scenario where ozone has oxidized, taken an electron away from M, so we're left with M plus, and this O3 dot minus. So perhaps that would look like this with the methanol here, CH3OH, plus ozone. We would end up taking away one of the hydrogens there and getting CH2O. Excuse me, that would be two of the hydrogens. Plus oxygen plus H2O. Okay, so that might be the net reaction with methanol. Okay, and another thing to note here is ozone itself scavenges hydroxyl radicals. So when we start talking about these advanced oxidation processes, you might start recognizing that things feel very circular, and there's quite a lot going on, and a full characterization of a system requires quite a lot of analytical chemistry and some understanding of many steps that are happening in maybe femtoseconds or something. So it's a very rapid processes, a lot of transient species that you could really only observe if you had very sophisticated tools in order to do so. And sometimes you just have to say, well, if I add this one thing that I know for sure reacts practically instantly to prevent this one thing, or maybe do a reaction where you don't have any ozone or you don't have any OH minus or something like that. Sometimes you have to be very careful in order to set up your situation to rule something out in order to show for sure, hey, this is the step in between, because otherwise you may just think, some chemistry magic is happening and you just don't know, because they're very rapid, very complicated. So a few rate constants just to sort of show that point. Ozone, you could look at it reacting with all sorts of different products, and here we have rate constants for the oxidation of select organic compounds by ozone and OH radicals at ambient temperatures. Okay, so we have a couple of rate constants here. On the left would be ozone, and on the right would be the hydroxyl radicals. And so if you take, for example, the first couple here, algal products, so maybe harmful algal toxins that you might have during a harmful algal bloom, and you take a look at the reaction rate constants with ozone, and this is per molar per second. Some of these are less than 10 for microcystin, that's one of the major toxins. 3.4 times 10 to the fourth for ozone. Now, if you then look over here on the right, for hydroxyl radicals, they're in the billions, right? 8 times 10 to the 9th, 2 times 10 to the 10th. Very rapid. The deal is, though, that we typically don't have very many hydroxyl radicals at any given time because they react so quickly with everything, right? So it's not like we have a high concentration of OH radicals. If we did, that would be very likely literally explosive, all that energy being released all at once from these reactions that would happen so quickly. But you could take a look and you could kind of see what all ozone is good at degrading. So for pesticides, it's apparently pretty good at dinoseb or whatever that is. Of course, hydroxyl radicals are much faster. For a lot of them, ozone is not really doesn't really do much, right? So tetrachloroethene, ozone is quite slow with. Hydroxyl radicals are still 2 times 10 to the 9th, right? So that's pretty typical. You can take a look at all of these, and maybe if you have some specific application, you would need some information there. So just wanted to kind of point that out. Okay, so for what we would call typical advanced oxidation processes, or, like I said earlier, ozone's sort of on the verge between an advanced oxidant because it can form the hydroxyl radicals, but it's also often used as a direct oxidant itself for disinfection or other. Okay, hydroxyl radicals. Those are the meat and potatoes. There's a few other radicals that can be common, but hydroxyl radicals, whether that's peroxide in UV, peroxide with iron for the Fenton reaction, ozone with OH minus. You could do photocatalysis with a semiconductor material. You could have these Fenton reactions. So whatever the case, there's each of these ones form hydroxyl radicals. There are some other options I'm going to mention. We can create reactive halogen species. So if we photolyze chlorine or bromine, something like that, we can create radical chlorine species and whatnot. We can create something called singlet oxygen, which this is not technically a radical, any more so than the molecular oxygen we breathe is kind of actually a diradical, sort of. The oxygen that we breathe is in a ground state, ground triplet state. We could call it 3O2. That little 3 is denoting the spin configuration of the electrons. That's pretty unique, but that's just the lower energy level for molecular oxygen. So if we excite it, it ultimately confines the electron spin into just one arrangement, and then we end up with a molecular oxygen species that is highly reactive. I did most of my PhD work on single oxygen production and using that as a tool for disinfection. And that is longer lived than hydroxyl radicals. It doesn't react quite as strongly with just anything and everything. So it lasts a little bit longer in solution. So if we had a lifetime for OH dot something like 1 nanosecond in water, then the lifetime for single oxygen in water is something like 5 microseconds. Okay, so lives typically about 1,000 times longer, still in the microseconds, so it still doesn't move too far away from where it was generated. But it's pretty interesting, and there are several different dyes and things, even some food colorings that can photosensitize the production of single oxygen. It's pretty interesting. Quenching reactions I've mentioned and we'll go into further, but dissolved organic matter, whether that's naturally occurring or maybe this is some stuff that happens to be in wastewater from all the microbial activity. If we're going to use an advanced oxidation process in one system or another, we probably need to concern ourselves with what's the quenching reactions, what are they going to look like, how can we deal with them in the scenario in the presence of dissolved organics. There are some inorganic constituents, just like with chlorine. We talked about sulfite being a scavenger. Similar scenarios, bicarbonate is a quencher for hydroxyl radicals. There are several different things that can interfere and give us effectively a lower amount of useful radicals given these quenching reactions, competing for them. Okay, so reactivity with organic compounds. There are several reactions. We could have hydrogen abstraction, and this is, context of hydroxyl radicals here. When we have saturated compounds, there's several equations in the book, so if you wanted to take a closer look, you can feel free to see these here. You could have an OH addition. So for unsaturated bonds, you just add the OH directly to the compound, and that's going to be an oxidation reaction in some sense because the OH radical wanted to take an electron, but it also kind of added itself to the system. Actually, I have the equations right here. And then in some cases, we have sort of redox type chemistry where things might cycle. Occasionally, we even get a radical species at the end that could then ultimately lead us back to another hydroxyl radical if the chemistry goes in the right direction. So sometimes you will have propagation reactions with some organic compound where, and this is something, if you ever hear about depletion of the ozone layer, this is how it works. You have some radical that interacts with whatever compound was causing this catalysis. So you end up destroying an ozone, reacting with this compound. It doesn't kill the compound. That compound then reacts with, let's say, oxygen to create another radical that would deplete another ozone molecule. And it would take many cycles of that before randomly this, maybe it's a fluorinated hydrocarbon or something, ends up reacting with something and is destroyed and can't do that anymore. So there's catalytic processes in some scenarios, but not too many. Okay, so the reactivity and lifetimes, I mentioned this just now. There's about the lifetimes, very, very short. There's a great reference manual sort of thing, paper. If you ever need to know reactivity between hydroxyl radicals, hydrated electrons, different ones of these radicals, it's a very large review paper from 1988 that summarizes a whole bunch of literature on it and provides a very nice readout of all of these reaction rate constants for all sorts of different things. Here we have benzene and some other compound there. And they list the pH that it was tested at and any comments and the reaction rate constant that that paper found. For these reactions, we often would say, for reactions that are diffusion controlled, it means we have some limit to how quickly our molecules can meet each other, right? So diffusion controlled. And in the sense, when we're considering our radicals, they're reacting, most of these, with the solvent itself and just generically reacting. I mean, chlorine will react with the solvent, but it's very slow, right? It'll have just natural decay. So if you left chlorine in a sealed dark bottle at room temperature for a few days, that will be dropping. It might not reach 0 in a few days unless it was quite warm. And if you had it in a refrigerator, it would stay, and it was dark, it would probably stay pretty active for a long time. But the lifetime we can think about for most of these radicals is something like 10 to the minus 7, maybe less for some of them. Yeah, and so it's going to depend a bit on the solute concentration itself, if there's something that's reacting with it. So I don't recall what exactly I was meaning by all this, so I'm just going to kind of ignore that. But my point is, it kind of gives you an idea of how long something's going to last, and if there's I'm sorry, the lifetime of a radical type solute would be 10 to the minus 7 if the that specific radical was concentrated to the millimolar concentration, which would be way higher than we'd ever expect for a radical, given that the lifetime is so short. Okay, I want to draw your attention to this example. We're not going to work it, but it's a good example of how we would need to combine our reaction rates and deal with them if we were to really characterize multiple reactions all at the same time. So I'm going to read through the example and then show you a few highlights of the solution here. So example 1014, this is page 472 of the book, says relevant chemical reactions for the oxidation of atrazine by ozone and the associated second order rate constants are given later. The first reaction is direct oxidation of atrazine by ozone. The second and third describe creation of hydroxyl radicals from ozone, and the last describes the oxidation of atrazine by the hydroxyl radical. So first, it's a direct reaction. Second, here's this ozone plus OH minus. And third, here's this ozone plus the, I guess that might be a hydronium ion. I don't remember the exact name. Yielding hydroxyl radicals, a superoxide radical anion, and oxygen. And then finally, this OH radical plus atrazine. Reaction rate constants for each of those, and we we would then think to ourselves, well, if we want to know how much hydroxyl radical, we need to know how much of this stuff we have, which means we need to know how much of this stuff we have, and we need to know how much pH we have, or OH minus. Excuse me. And all of that, we also need to know how much ozone we have at a given time. But the ozone is continuously reacting away. So we can see very easily that this is going to be a very challenging condition if we really need to get into it. And so the problem says determine the atrazine concentration as a function of time over a 10-minute period in a batch reactor at pH 6 under the following circumstances. And first it says the initial atrazine is 10 nanomolar, presence of 50 micromolar ozone, assuming oxidation occurs only by the direct reaction with ozone. Okay, so that part's pretty easy. That's just saying take this one, right? Specific conditions, use this one, no problem, we could solve that, right? We could set up a mass balance, it's batch reactor, it's going to be pretty simple. The next one says, okay, how about the same conditions right there, but considering direct oxidation by ozone and indirect by reaction with hydroxyl radicals that are formed from ozone decomposition. Okay, so now we need it a little more complicated. Now we have to consider and find some concentration here, and our mass balance would be essentially the total rate of atrazine degradation would be the rate from ozone directly plus the rate from hydroxyl radicals, right? We could set up a mass balance that looks like that. Fortunately, it's a batch reactor, keeps things pretty simple, and we could solve that way. Okay, the same condition, so the third case was the same conditions as the previous one, except a different initial ozone concentration, and then the final one, we have another case, but this time the atrazine concentration changes. Okay, so let's take a look back at the solution. It calls back to chapter 3 and says the mass balance here for any chemical I is essentially dC for I changing dt is the sum of the reactions with I. So that's kind of what I just showed, right? That's this highlighted here. The summation of each of those reactions. Applying this idea to 4 chemical reactions of interest here but because we have to do this for ozone, atrazine, hydroxyl, and this hydronium, I'm just going to call it that. Does anybody remember? HO2 minus. Okay, no problem. We obtain rate expressions as shown, and I'll bring those in a second. Okay. Let's see. All right. So then we have these 4 different reactor or reaction systems, right? For dC of ozone, dt, we have those reactions. For dC for atrazine over time, we have these 2. For hydroxyl radical, these 2, and for this other guy, we've got these 2. And the book goes on to say, well, with some nice software, we can create graphs like these. And I think we could use Excel to do like a stepwise numerical solve for this type of a system. But it's difficult, and the tricky thing is you have to do it like simultaneously, because each of these are depending on one another. So it is a pretty big challenge. I think there might be one of your homeworks ask you to do something like this. So give it a shot. I'm going to be pretty lenient, but I want you to try going through the process if I didn't remove that problem. So if you do find that in the homework, that's my expectation, that you give it an honest effort and see about doing this in stepwise time. So they have time in seconds here, and you see they've done maybe 600 steps, 1 second each or something like that, to track these. So this is something that is possible. Take a look at this example, and I think the one after follows along with it, and maybe changes the pH or something. So I wanted to show you that and give you some appreciation for how this would have to work, tracking essentially the changes in each of these. And then you could use each stepwise to calculate, okay, well now the ozone concentration should be about this given these reactions, which means this one over here is going to be about this at second number 3, right? From second number 2 to second number 3, we'll step through the system. Okay, so back to hydroxyl radicals. Specifically, we've got, we could take a look at reaction pathways. In this case, we have a schematic showing a reaction of methanol, a substituted benzene, and tert-butyl alcohol. So 3 different ones, and we can consider when, under what cases are the hydroxyl radicals going to propagate or just be quenched. Okay, tert-butyl alcohol on the far right here, I'll tell you right now, is known as a strong quencher. It reacts quickly with it, and it has no propagation of radicals afterwards, which is why we'll use it a lot, and you've probably seen that. If you've worked with any sort of radical chemistry, you may have worked with that. Okay, so let's start there then. So we have reaction with the OH. It adds, and the radical, we see it there, and we get water from that. That then dissociates to have an oxygen that leaves, and we're left with this guy, which ultimately, I think that this radical might come off as an OH. I'm not sure where it goes exactly from there. Maybe it just keeps it. But essentially, there's no superoxide radical that comes out, and so no way to regenerate or recover more OH dot. That's in contrast if we see methanol here. We get the reaction. We get water plus this radical guy. If that reacts then with oxygen, and I'm sorry, that's what was happening here. We have a reaction with oxygen to form this molecule, and then that will decompose into an H+, a superoxide radical anion, which is O2 dot minus. So it's a molecular oxygen, but it's a radical. And this product, now this product is something that was destroyed essentially, so it no longer has the same features. It wouldn't be able to do it again, but the fact that we have the superoxide radical anion does mean that we can generate from some radical reactions more hydroxyl radicals. Okay, so that's kind of what this is showing. A similar thing happens with this benzene group, substituted benzene, where we had some benzene attached to some other functional groups. Reaction with that would add an OH to it, and ultimately oxidize it a bit, but we're still left with, at the end of the day, we're going to have this oxygen radical leave again, and then we'll be left with a benzyl alcohol of some sort. So we've added that OH group to the benzene, and it's still attached to something else. And then we have the superoxide radical out there again, and which can then go back and form more hydroxyl radicals. And then this guy might go through the similar process. Eventually it's going to be oxidized, but you see it's kind of looping here. Some reactions, some changes, we're getting maybe some oxygen released or some hydrogens released, things like that, but we can see the radicals can propagate in some scenarios here. Okay, UV and peroxide is one of our potential reaction pathways to do an advanced oxidation process. This one's pretty common. Hydrogen peroxide is relatively easy to use. You can generate it on site or you can ship it. It's stable enough. It is pretty hazardous if you have high concentrations, but at the same time, you've seen it at your local store and have used it probably when you had a little cut or something. It's in those bottles, it's probably between 1% and 3% hydrogen peroxide. So in water, it's stable enough. If you shine light on it, it will start decomposing typically. So our typical mercury lamps at 254 can do a decent job at splitting it. And if we take a look at the absorption spectra, so if we're giving that light right around here, we can see that that's a pretty good spot within the absorption spectra. If we shift to maybe UV LEDs that shine a little bit off to the side, it's not going to be as efficient. So not the best candidate for changing wavelengths unless we went lower, perhaps. There's some challenges with that. Okay, so what's going to happen then is each peroxide can be split into essentially 2 hydroxyl radicals. So it's very efficient, convenient. And then there's another scenario, though, where we might have some concern because we could have HO2 minus. That's going to be an equilibrium product if we treat peroxide as an acid base, where one of those protons could leave. So under basic conditions, we have more of this HO2 minus, and that's actually absorbs a little stronger. Maybe it's something like this, if we were to look at the absorption spectra. Probably should bring it down to just 0, not below 0. So that would probably look something like this. This is the HO2 minus. And so under those conditions, we get some better UV absorbance. Okay, and it also can undergo some similar reactions. And so it turns out that applying it at a basic pH is actually a little better for that reason. So we kind of end up with the same products, but we can do that. So perhaps that would be a case to use different lights. And I'm just sketching something here. It might not actually have such a redshifted, as we would call it. If we shift to the right, that's a redshift in our absorption spectra. It might just be, this is a normalized absorption, and so maybe it's actually just meaning it would be higher than the peroxide at 254. That is what this is saying. So I'm guessing maybe it might have a different wavelength up higher, but yeah, mostly it's just that it's a little better at that. The quantum yield, what this is referring to is how many hydroxyl radicals do we get per photon that was absorbed, is actually above 1 for this case, whereas, so it's about 1.1, and that's because it's not always 100%, we're not always getting this two for 1 deal. And in the case of this guy, we wouldn't expect to. Okay, we can take a look at the sources and sinks for peroxide photolysis. If we have some peroxide plus UV generating hydroxyl radicals, we have then some pool of hydroxyl radicals, then we could take a look at how reactions go from there, right? So this is the type of diagram. We'd have something that looks like this or something that shows the same type of information pretty much any time we deal with radical chemistry. Maybe this is photochemistry, maybe this is advanced oxidation, but you really want to track where things are going, where do they stop, where are they produced, do we have some amount that we can draw from, and so we could take a look at all sorts of different places where these are going to react. So this is just another one of these. Notably, bicarbonate, HCO3 minus, will react, and you will have no radicals forming after that. You'll have a carbonate radical, but that's not super useful in solution. It doesn't react with a whole lot. It's not going to give us much activity or useful action. It's just going to take away a lot of our hydroxyl radicals. So if we have a lot of bicarbonate, so a lot of alkalinity, we would want to either remove that or adjust the pH so we don't have to deal with that. Okay, so there's some other things we could take a look at. Reactions with methanol. That's like we showed earlier. We can get superoxide radical anions out from that, which would end up being another source of peroxide or of hydroxyl radicals. Okay, I mentioned the pH dependence. So if we have reaction yields for ozone and OH minus, so coming back to the ozone case, if we're going to use ozone for an advanced oxidation process, if we push the pH to basic conditions, then our ozone will then form some hydroxyl radicals. So we have pH 8 here, and we're taking a look at how much of this is atrazine again, degraded by ozonation. And here we see it's degraded pretty well at pH 8 and not so well at pH 6. That's because ozone itself is not reacting particularly fast with it, but ozone plus the OH minus gives us some hydroxyl radicals that are working for us here. We can see the same thing over here in this the second plot. And I think that's different concentrations of ozone. Okay, we can also take UV and do ozone photolysis. So we're splitting ozone with UV. Again, this is kind of what happens in our upper atmosphere. So we could take a look at how much light does ozone absorb and what kind of reactions come out of that. And so we have a UV-vis spectra here where we see ozone absorbing here up to about 350 nanometers. It's really not quite there, but it's absorbing light in the UVC and UVB range. We also have the molecular oxygen here that does absorb even up to 250 range, although it's not absorbing much by then. And then we also have ozone absorbing out here in the visible range a little bit. It's not strong, right, because we don't see it as a color directly, but it can absorb some of the light. The deal is the different reactions here are going to depend on what energy the photon had. So the reaction we're really interested in is ozone plus UV forming this oxygen singlet, the O1D here, and molecular oxygen. That occurs at about 310 nanometers or lower. So that's really talking about this range of photons. So at that range, we have enough energy to split it into these particular products, and this oxygen singlet is capable of then going to form our hydroxyl radical. So that's this guy here. We can actually get similar oxygen radicals that don't have the same energy. This O3P is not actually capable of undergoing the same reactions. So there's a bit of an energy level difference there. So this is the one we're interested in, and then we can get the formation of our hydroxyl radicals and all that we're interested in. This can essentially the way this will work is then that can react with water to create peroxide, and then we know the peroxide can form hydroxyl radicals, and so on. Okay. And also noting the quantum yield here, so we can get some of this oxygen singlet also up in the visible range for ozone photolysis. So we do have a little bit of ozone in our lower atmosphere. It's an irritant. Some of that can actually generate hydroxyl radicals, but if you take a look at the quantum yield for this UVC or UVB energy down here, the quantum yield is 90–95%, whereas the quantum yield for visible light, that 410 nanometer range, is really quite low. So UVA, that's this range right here. It's very low. It's not going to be common to get the radicals from that. Okay, we could take another look at sources and sinks. So if you're curious, you can see this here. This one's getting UV, or the UV plus ozone system with some pool of hydroxyl radicals again, but also some scenarios where we have ozone here, whether it's formed or whether it's generated on purpose or by byproducts of other reactions that are happening. So again, we can take a look at these things and think about where our radical chemistry ends or how it cycles. Okay, so I'm like I said, just blazing through here. Hoping this is not too much all at once. I'm going to talk a little bit about a few special topics, touch on some research briefly. Again, I don't know how far I'm going to get, but we've got 15-20 more minutes. So semiconductor photocatalysis. This is another advanced oxidation process in a sense, where we have a photocatalyst. Let me see. Yeah, we excite it by light. We essentially get a separation between an electron that was hanging out in the material, and then it gets kicked up into what we call the conduction band, and that leaves a hole behind. And if they are successful at separating and the electron finds some new home, perhaps through various reactions with oxygen to create this guy here. I've talked about it a lot. This O2 dot minus, that is called superoxide. And fully we'd call it superoxide radical anion. And as we've seen already, there's various reactions with that can get us to hydroxyl radicals. By itself, it can be a pretty strong oxidant. So if we're applying this in an effort to degrade some contaminant or something like that, there's all sorts of potential here, and with the intermediates in between. On the flip side, the hole that's left over in the valence band will also act as an oxidant directly. So the electron here can react with stuff to form highly oxidizing stuff, and this hole can act as an oxidant directly. We can also have reduction reactions. I mean, essentially that's what's happening here to get the superoxide radical anion. We've reduced oxygen. So there's some reduction process here, which would make sense if we're left with this hole that really wants to take an electron from something. But both of these situations are leading us ultimately to hydroxyl radicals potentially, right? Now, the hole here could also react directly with some organic compound. So there's a lot that could go on here. What's really interesting, though, is that this system is actually inevitably on some surface. So we have some compound, or not a compound, some material surface that we're using for this, and then some compound that we want to destroy has to be in some proximity to this, especially because we recognize these hydroxyl radicals can't really travel very far in a few nanoseconds, right? On average, they're not going to travel very far because they're going to react so quickly. Okay, so then, and by the way, if a lot of times in reality, this electron in the hole would just recombine and release a bit of heat. So there's a lot to do with photocatalysis that aims towards preventing those from recombining. So when they successfully get away from each other and go and react, then we have some interesting action. There are many different types of photocatalysts. There's even some that are sort of organic in nature or not 100% inorganic, but most of the time we're talking about semiconductor, like inorganic semiconductors. So here's a few examples of experimentally reported quantum yields for destruction using TiO2. And so there's different probes, chemicals that we would use to determine how much hydroxyl radical essentially was generated. And so we could take a look. There's different wavelengths that people use, different probes, and all these things. One of the difficult things about comparing photocatalytic systems is recognizing the differences between, okay, what kind of material did you use? What kind of light source did you use? What were your solution conditions? There's a lot that can change, and a lot even if you're doing a just batch scenarios, let alone applying it to a flow through a system complicates things even further. Okay, a few big picture comments. So we're all excited about, hey, photocatalysis, it's the next, it's a sustainable water treatment, hooray. But when you stop and think about it, like I was saying, there's a lot of complexity that goes into this. Okay, you've got the solar energy. You have to know, okay, how much of that is useful, how much of that can activate your catalyst or sensitizer. So you could then say, all right, well, we have some number of photons per area, per time, some useful amount of energy. And there's a good paper a few years ago by my PhD advisor and several others that really took a look at this on a big picture and said, well, we can take the photocatalyst route. We're essentially going for some steady state concentration of hydroxyl radicals that can give us some known contact time to deal with, and therefore we can get some estimate of what's our water treatment look like per liter given the amount of sunlight we could use for that. And that's limiting it to just sunlight, just the sunlight analysis. So how to use solar water treatment. Another option would be to use a photosensitizer. I mentioned dye materials. This is what I did most of my PhD work on. Producing single oxygen, same process, same principle. We have some concentration that can be useful as a disinfectant. You could have direct solar disinfection, SODIS is what we would call it. That's not super effective. That's primarily using UVA, inducing this type of reaction in whatever molecules happen to be in the organisms. So it's relying on creating some oxidative stress. It takes a long time. 6 to 8 hours in direct sunlight gets you an improvement in water quality that's not a huge improvement, but it's some. We could then consider using some fancy materials to do what we call up conversion, take these UVA photons to ultimately create UVC photons. That's not been very efficient, but it's something that is an interesting idea. Or you could take a solar cell and generate some electricity and then apply UV light. Okay, so probably one of the most straightforward. They went on to really think about all the different stuff here. And so if you're curious about solar disinfection generally, definitely take a look at that paper, Beyond the Pipeline, Assessing Efficiency Limits for Advanced Technologies for Solar Water Disinfection. Okay, so that's very interesting. I thought there's a related one where a similar group of a whole bunch of researchers in this field, and this, by the way, this is my PhD advisor and a drawing that he made of himself for this paper. He's a fun guy. It's Jay Hong Kim. Put out a bigger paper here about kind of what's the technology horizon here. Is it going to work? Is it ever going to work? What's going on with photocatalysis? Because we've been actually hearing about it since 1970s, and it's really not achieved too much practical application. So they go into it a little bit more here. This is where I pulled some of the data a minute ago. Really just analyzing the different aspects. What are the limitations? Why don't we have true practical applications with photocatalysis? There's maybe a couple commercial slurry reactors that are not super efficient and very niche in their application. Maybe make sense for a very particular wastewater stream, but really, practically speaking, there have not been formal, this technology has not become realized as practical, right? So that's ongoing work, and I think where very important work is happening in terms of how do we get it to a point, how do we design a reactor that solves for the fact that you have to get light to your whole catalyst, but you also have to get your molecules to all the catalysts, but you also have to have water flowing through. There's a lot of technical challenges from an engineering perspective to solve in order to effectively use photocatalysis, instead of just dumping some in a bottle and then realizing, well, now I have to filter out my catalyst, so I might as well have just filtered my water, right? Because that's, in essence, that's part of the limit. It's like, well, doing all this work to use it, but I could have just filtered it or chlorinated or whatever, So, okay. Another topic here, Fenton reactions. So I mentioned peroxide earlier. That's usually what's used when we consider Fenton reactions. And so how many of you have used hydrogen peroxide to clean a cut or scrape or something? Okay, most of you. What happens when the peroxide touches your blood?
It bubbles.
It bubbles, right. You see reaction. It's a chemical reaction, right? That's the Fenton reaction. Okay, moving on. Basically, you're producing hydroxyl radicals. It's going through this Fenton reaction. You're taking your Fe2 plus in your blood, and you are essentially reacting that with hydrogen peroxide. The iron is oxidized, and you end up with a peroxide radical. This is very fast and does a pretty good job, happens pretty quickly. And we see that when the Fe3 plus reacts with peroxide, then we go back to Fe2 plus and release one of these guys, I'm going to call it hydronium radical. I'm probably wrong, but maybe I'm right. And then the Fe3 plus can react with superoxide radicals, which this can dissociate, this HO2 dot can dissociate into superoxide radical anion. And then what we get here is iron 2 plus and oxygen. There's the bubbles, right? Oxygen bubbles coming out, all the fizz. And so this is rather cyclical. If we have iron and peroxide, we will be going through this reaction repeatedly, or this sequence of reactions. So there's quite a lot there. There's a lot of, it's a pretty well documented study. It's used occasionally. You could consider the fact that if we're going to use, let's say, ferric chloride or something like that for coagulation, you could also dump some peroxide in there in order to generate hydroxyl radicals and do some oxidation while you're doing coagulation, right? So it's interesting. I think it does find some uses. You'll definitely see it in the literature, in different scenarios. Maybe you're even in natural systems. Sometimes it becomes relevant. There's some naturally forming peroxide in natural waters. Not huge concentrations, but it's out there. So that's all things you could consider. Okay, so some quenching reactions. Mentioned it several times, but generally what we would think of as a quenching reaction is some inorganic compound or maybe some organic, but so for the inorganic case, we'd look at it as we've oxidized that inorganic compound, and then we have hydroxide anion. So a hydroxide is not reactive, right? OH minus is just in solution. That's not the super reactive stuff. It's when it's the missing an electron, it's OH dot, that's the reactive. We could have weak bases. This is our bicarbonate, phosphoric acid in the dibasic form. Each of these could react, and essentially what we would get as a result in the first place would be a carbonate radical. I mentioned that earlier. Those are not very useful in terms of radical chemistry. They are reactive, but not very for a radical. So maybe they do a little bit of something, but it's definitely not going to return us to a point of having more hydroxyl radicals again. like some of the other reactions do. Same thing with phosphate. Typically, we don't have a lot of phosphate in most of the waters we deal with, so that's not as commonly relevant. You could have other unwanted reactions with chlorine, or chloride rather, with sulfite, so reduced sulfur groups. Those could quench our system. Okay, I kind of already mentioned the photocatalysis, the limitations, but specifically that paper that I mentioned highlighted a few specific issues. So quantum yield for one, light absorption, so you have to manage the way your light travels and arrives to your photocatalyst. You have to make sure that your catalyst is supported, it's stuck onto some system in a way that's not going to just fall off. And you have to do that in a way that's not going to kill your quantum yield, because maybe you attach it chemically, you chemically bond something, but then that kills the photosensitizer's ability to sensitize single oxygen, for example. Or perhaps it's preventing, the way you've attached it has now prevented surface area, or something. There's a lot that you have to deal with. The reactive oxygen species, ROS, how far it's going to diffuse, so you have to make a reactor that's got really good surface area contact with the water that you're trying to treat. And you have to deal with these quenching by non-target compounds. So when I first prepared these slides, I highlighted this paper. Today I would probably highlight the research project Mary's working on. I don't have slides for it right now, but this is the type of project that we're working on with Dr. Kevin McPeak, her advisor, and I'm excited about it because it is tackling these types of problems. Here I'm just going to show you some other people's interesting idea. They took essentially a fiber optic cable, removed some of the sheathing that protects the light and causes it to reflect internally and keep it inside. So they removed that and coated the outside of that with photocatalyst so that the light would travel and start leaking out. You can kind of see it in this picture. The light starts leaking out of the fiber optic cable. It's still traveling through it to some extent, but some of it's leaking, and it's leaking straight into the outer coating, which is photocatalysts. Now, that's a pretty neat idea. Seems like it might work pretty well. However, the fiber optic cables typically are, if you make them out of glass, that's good for light transmission, and that's good for resistance against hydroxyl radicals, but it's very fragile. So really the only reason that fiber optic cables, a long, thin piece of glass, can stay intact is actually that protective coating. So if you bend this at all without that coating, then it's just going to shatter. So this case, either you need some fancy plastic that transmits light pretty well, but also is resistant against the hydroxyl radicals that would typically attack an organic molecule, or you have to get clever with some way to keep it protected or straight. So there may be some ways to do that. That seems like it could give you a high surface area and good light transmittance to your hydroxyl or to your photocatalysts. So it solves some of the problems, and is the type of thinking that I think is the right direction. Like I said, we've got an ongoing project. It takes a bit of a different approach and also uses UVC light, or has the opportunity to, so we can get the combined disinfection plus advanced oxidation stuff happening. Okay, we already showed that. Okay, some other AOP will end here. This is ongoing research topic for my group. We've got reactive halogen species. So we're taking chlorine, photolyzing chlorine, and essentially if we take a look at HOCl and OCl minus, chlorine photolysis as an advanced oxidant has not been super popular in the past. It's like, well, we can chlorinate, or maybe we'll use the peroxide plus UV for advanced oxidation. And part of that reason is HOCl absorbs light at our 254 wavelength, but not a whole lot. And OCl minus doesn't much either. But it turns out that if we shift the wavelength a bit and start getting a little more of the OCl minus involved, what we can get, we can create this oxygen singlet that we mentioned earlier, which can then react with water to form, well, one, we could form hydroxyl radicals directly, but we can also actually end up forming ozone by reaction with this version, the O3P. So we have, excuse me, we end up forming ozone in some cases for our system. And then the ozone can be reactive and potentially could also form some OH minus. So we've been doing some experiments where we are using light that's kind of in this range or potentially this range and comparing that with light from this range to see how things are going. I mean, and I drew all these very poor depictions here, and I could have just drawn your attention here. So essentially, we have a lot of chemistry to explore and potential applications. And some of the things we're looking at is, can we purposely create ozone so that it's a little more selective? We can let the radicals live a little longer. What happens if we pulse the light? Is that going to give our radicals a little more time to persist before undergoing all the other chemistry? Can we have better quantum yields? And as we look towards the future, another thing we're looking at is, well, this is really neat, but what about chloramines? What about monochloramine? Can we do photolysis with that? What does the UV vis spectra look like for that? How reactive or effective would ammonia type radicals be? Amine radicals and such. So that's all very interesting to us. There's some obvious risks about, are we making chlorinated byproducts? There's an important question there, but also how would that compare to just chlorinating? So it might actually be, there's potential that there'd be less. Okay, so I'm gonna leave it there. We'll go through the homework on Thursday. And by then I should have an update for you about posting the exam. All right, see you then.